Today's video on Imagine will be the most excited one, can you guess? Well, stay tuned. In this video we will be exploring our planet Earth's layers inside and out. Earth's layers can be assigned according to chemical composition, what they are made of, or mechanical properties, rock strength and elasticity. Earth is made up of several layers. Layers based on chemical composition are the core, mantle, and crust. According to mechanical properties, Earth's layers are the lithosphere, asthenosphere, lower mantle, also known as mesospheric mantle, outer core and inner core, according to phys.org, opens in new tab. We will explore each of Earth's layers in more detail as we journey from the center of the Earth out to the layer we call home. Inner core. At the center of Earth is a solid iron inner core. The hot dense core has a radius of about 759 miles, 1,221 kilometers, and a pressure of about 3.6 million atmospheres, atm. Temperatures in the inner core are about as hot as the surface of the Sun, about 9,392 degrees Fahrenheit or 5,200 degrees Celsius, more than hot enough to melt iron, but the immense pressure from the rest of the planet keeps the inner core solid, according to National Geographic. The primary contributors to the inner core's heat are the decay of radioactive elements such as uranium, thorium, and potassium in Earth's crust and mantle, residual heat from planetary formation, and heat emitted by the solidification of the outer core. Earth's inner core rotates in the same direction as the surface of the planet but rotates ever so slightly faster, completing one extra rotation every 1,000 years or so. Outer core. Earth's outer core is sandwiched between the inner core and the mantle. The boundary between the inner and outer core is known as the Learman seismic discontinuity, according to study.com. The outer core is approximately 1,367 miles, 2,200 kilometers, thick and composed of liquid iron and nickel. Temperatures in the outer core are between 8,132 degrees Fahrenheit and 9,932 degrees Fahrenheit, 4,500 degrees Celsius and 5,500 degrees Celsius. Earth's interior is gradually cooling over time. As it cools, the liquid outer core crystallizes and becomes part of the solid inner core. Remarkably, the inner core grows by about 0.039 inches, 1 millimeter, every year, which equates to the solidification of 8,820 tons, 8,000 tons, of molten iron every second. The solidification of the outer core releases heat which drives convection currents in the outer core that helps to generate Earth's magnetic field. The swirling motion of the outer core generates Earth's magnetic field in a process called geodynamo. According to NASA Earth Sciences, magnetism inside Earth's core is approximately 50 times stronger than it is on the surface. Eventually, the entire core will solidify and Earth's magnetic field will cease to exist. That will be bad news for our planet as the magnetic field protects us from harmful cosmic radiation. We still have a few billions of years of protection left though. Mantle. The mantle is the largest and thickest layer of Earth, making up 84% of the planet's total volume. The mantle can be further divided into the upper and lower mantle, also known as the mesospheric mantle, with the upper mantle containing two distinct regions, the asthenosphere and the lower portion of the lithosphere. The lower mantle refers to the layer between the outer core and asthenosphere. It makes up 55% of Earth by volume and experiences pressure from 237,000 atm to 1.3 million atm towards the outer core. Heat and pressure in the lower mantle are much greater than in the upper mantle. The immense pressure keeps this layer solid despite the high temperatures capable of softening the rocks, though geologists are yet to agree on a definitive structure of the lower mantle. According to the Gemological Institute of America, diamonds are forged within the mantle approximately 93 to 124 miles, 150 to 200 kilometers, below the surface. They are brought to the surface by magma churned up from the depths due to tectonic processes such as plates splitting apart. Asthenosphere. The asthenosphere is a 110 miles, 180 kilometers, thick layer of the upper mantle that sits between the lower mantle and the lithosphere. The term asthenosphere originates from the Greek asthenes, meaning weak. The weak layer is denser and more fluid than the lithosphere above, and pressure and heat are so high that rocks in the asthenosphere flow extremely slowly with a highly viscous molten fudge-like consistency. Temperatures in the asthenosphere are around 2,732 degrees Fahrenheit 1,500 degrees Celsius according to the educational science site Earth How. Rocks in the asthenosphere are on the verge of melting, but due to the high pressure, they behave in a more ductile manner according to the Geological Society. Lithosphere. The lithosphere is the outermost layer of Earth, composed of the crust and the brittle part of the upper mantle. The term lithosphere is derived from the Greek words lithos, meaning stone, and sphaira, meaning globe or ball. Lithospheric temperatures vary from 32 degrees Fahrenheit 0 degrees Celsius at the crust to 932 degrees Fahrenheit 500 degrees Celsius at the upper mantle. Lithosphere is broken into large lithospheric, also known as tectonic, plates. Convection currents in the lower mantle and asthenosphere help to move the rigid lithospheric plates according to Earth how. The slow, floating movement of the lithosphere on the asthenosphere drives plate tectonics and subsequent processes such as earthquakes, volcanic eruptions, and the formation of mountains. The lithosphere can be further divided into oceanic crust and continental crust. The boundary between the brittle part of the upper mantle and the crust, both oceanic and continental, is known as the Mohorovii discontinuity, MOHO. The MOHO depth varies from about 5 miles, 8 kilometers below oceanic crust to 20 miles, 32 kilometers below continental crust. Oceanic crust and continental crust differ in their composition, density, and age. Oceanic crust is primarily composed of dark basalt rocks rich in elements such as silicon and magnesium, whereas continental crust is made of light-colored granite rocks containing oxygen and silicon. Oceanic crust is denser than continental crust, and when two lithospheric plates, one oceanic and one continental, meet, the oceanic plate always subducts beneath the more buoyant continental plate. The subduction of oceanic crust beneath continental crust continually recycles the oceanic rock back into the mantle below. This constant destruction is why oceanic rocks are rarely more than 200 million years old, whereas continental rocks, which face far less adversity, can reach a ripe old age of 4 billion. How do we know Earth's layers are there? Seismic waves can tell us a lot about Earth's interior, including where the lithosphere and asthenosphere are located. During an earthquake, primary, P, and secondary, S, waves spread out through the Earth's interior. Special stations situated around the world detect these waves and record their velocities as well as the direction of wave travel and whether they have been refracted, bent. Seismic waves travel faster through dense material like solid rocks and slow down in liquids. Relative differences in arrival times of waves at several recording stations reveal their velocities and subsequently the density of the material they have traveled through. S waves, for example, cannot travel through liquids and do not travel through Earth's outer core, implying that this layer is liquid. Hope you enjoyed the video. You could appreciate our humble efforts by liking the video and subscribing Imagine channel. See you on the next video.